You probably have a magnet on your fridge. It holds up a drawing or a shopping list. It just sits there silently doing its job. You can pull it off and stick it back on. You can slide it around. You can take another magnet and feel that strange invisible push or pull. It's a common thing. So common, we don't really think about it, but if you stop and really consider it, it's a kind of magic. What is that invisible force? Why does it work on the fridge door but not the wooden cabinet next to it? Why are some things magnetic and most things are not? The answer isn't simple. It's not one single thing. It's a story that starts with something huge, like the whole universe, and ends with something so small you can't even imagine it. The journey to understand magnetism is a journey into the heart of matter itself. It's about electricity, atoms, and a weird property of electrons that doesn't make a lot of sense at first. To get to the bottom of it, we have to start with a basic connection. Magnetism is a side effect of electricity. Not the electricity in your walls necessarily, but the fundamental idea of it. The thing that creates a magnetic field is a moving electric charge. If you have an electric charge, like an electron, and it's moving, it will generate a magnetic field around it. It's a fundamental rule of the universe. Think of a simple wire. If you push an electric current through that wire, which is just a whole lot of electrons moving together, a magnetic field will pop into existence around the wire. Turn the current off, and the magnetic field vanishes. This was a huge discovery. It showed that electricity and magnetism weren't two separate things, but two sides of the same coin. They are linked. So, a moving charge creates a magnetic field. That's our first big clue. Now we have to look for moving charges inside a regular piece of stuff, like a block of iron or a piece of wood. Where are they? They're inside the atoms. Everything is made of atoms. You, me, the chair you're sitting on, the air you're breathing. And every atom has a basic structure. There's a dense little core in the middle called the nucleus. And whizzing around that nucleus are tiny particles called electrons. Electrons have a negative electric charge, and they are definitely moving. This is where the first source of magnetism comes from. An electron orbiting a nucleus is, in a way, like a tiny loop of electric current. It's a negative charge moving in a circle, and just like the current moving through a wire, this orbital motion of the electron creates a tiny, tiny magnetic field. Each atom, with its orbiting electrons, can be thought of as a miniature magnet. This is called the orbital magnetic moment. So if every atom has orbiting electrons, and those orbiting electrons create magnetic fields, then shouldn't every single thing be magnetic? Why isn't your coffee cup magnetic? Why isn't your hand magnetic? The reason is cancellation. Atoms are complicated. Electrons don't just fly around in neat little circles like planets around the sun. They exist in specific energy levels or shells, and within those shells they tend to arrange themselves in a way that creates the most stable atom. Part of that stability comes from canceling things out. Electrons often orbit in pairs, and they move in ways that cause their individual magnetic fields to point in opposite directions. So one electron's magnetic field cancels out the other one's. Imagine two people swimming in a circle in a pool, but in opposite directions. The overall churning of the water is much less than if they were both swimming in the same direction. In many atoms, the total magnetic field from all the electron orbits adds up to 0. They all cancel each other out. This is why most materials don't seem magnetic at all. The potential is there, but it's all neutralized. But the electron's orbit is only half the story. And it's the less important half. There's another source of magnetism from the electron, something much more fundamental and a bit strange. It's a property called spin. When physicists first started to understand the electron, they found it behaved as if it were spinning on its axis, like a tiny planet. This spinning motion, because the electron is a charged particle, would also create a magnetic field. This is called the spin magnetic moment. Now the word spin is a little misleading. An electron isn't a solid little ball that is literally spinning. It's a point particle. It has no size. You can't actually point to its surface. The spin is an intrinsic, built-in property, like its charge or its mass. It just has it. You can't make it spin faster or slower. It just is. But this intrinsic property makes the electron behave exactly like a tiny, powerful magnet. It has a north pole and a south pole. This electron spin is the main source of magnetism in materials. It's generally much stronger than the magnetism created by the electron's orbit. So every single electron in the universe is a tiny magnet. This brings us back to the same question. If every atom is full of these tiny electron magnets, why isn't everything magnetic? Again, the answer is cancellation. Electrons, like tiny bar magnets, prefer to pair up. Inside an atom's energy shells, if there's a spot for two electrons, one will have its spin pointing up, and the other will have its spin pointing down. Their magnetic fields are in opposite directions, and they cancel each other out perfectly. It's a very stable, low energy arrangement. Most atoms in most materials have all their electrons paired up like this. The spin up of one electron is perfectly balanced by the spin down of its partner. The net magnetic field from their spins is zero. So for a material to be magnetic in any significant way, it needs to have atoms with unpaired electrons. It needs to have at least one electron in an outer shell that doesn't have a partner to cancel it out. This is the starting point. Having unpaired electrons is the ticket to the game. Now we can start to understand why different materials behave so differently around magnets. It all depends on what those little atomic magnets created by the unpaired electrons are doing. This leads to the different types of magnetism. The simplest type, and one that all materials have, is called diamagnetism. It's very, very weak. In fact, it's a form of repulsion. If you bring a strong magnet near a diamagnetic material, the material will be slightly pushed away. This happens even in materials where all the electrons are paired up. What happens is that the external magnetic field you introduce messes with the orbits of the electrons in the atoms. The electrons adjust their orbital motion to create a tiny magnetic field that opposes the external field. It's like the universe's way of resisting a change. This effect is in every single atom of every material. But it's incredibly weak. You need very powerful magnets and sensitive instruments to even notice it. Water is a good example of a diamagnetic substance. There's a famous experiment where scientists used a huge magnet to levitate a living frog. The frog's body is mostly water, and the water was being faintly repelled by the magnet, just enough to counteract gravity. So everything is at least a little bit diamagnetic, but it's not what we think of as magnetism. The next step up is called paramagnetism. This happens in materials that have atoms with unpaired electrons. Things like aluminum, platinum, and even oxygen gas. In these materials, each atom with an unpaired electron is a tiny permanent magnet. But at room temperature, all these tiny atomic magnets are pointing in completely random directions. One points left, one points right, one up, one down. They are all jumbled up like a disorganized crowd of people looking every which way. Because they are all random, their magnetic fields cancel each other out on a large scale. So, a piece of aluminum doesn't act like a magnet on its own. But if you bring a strong external magnet near a paramagnetic material, something happens. The atomic magnets feel the force of the external field. They try to line up with it like compass needles trying to point north. The thermal energy of the atoms, which makes them jiggle around, prevents them from lining up perfectly. But they do line up a little bit. A small percentage of them will orient themselves with the field. This causes the material to be weakly attracted to the magnet. As soon as you remove the external magnet, the thermal jiggling takes over again, and the atoms all go back to pointing in random directions. The attraction disappears. So paramagnetism is a temporary and weak attraction. This still doesn't explain your fridge magnet. A fridge magnet is a permanent magnet. It creates its own magnetic field without any help. It doesn't need an external magnet to be magnetic. This powerful, everyday type of magnetism is called ferromagnetism, and it's rare. Only a few elements on the periodic table are ferromagnetic at room temperature: iron, cobalt, and nickel. A few others, like gadolinium, become ferromagnetic, but only at very cold temperatures. So, what makes iron so special? Iron atoms, like paramagnetic atoms, have unpaired electrons. So each iron atom is a tiny magnet. But that's not the special part. The special part is what happens between neighboring iron atoms. In ferromagnetic materials, there is a very powerful quantum mechanical effect at play. It's called the exchange interaction. This is the real secret. The exchange interaction is basically a force that makes the spins of unpaired electrons in neighboring atoms want to line up in the same direction. It's not a magnetic force itself. It's actually related to the electric repulsion between electrons and quantum rules about how they can occupy space. The result is that it becomes energetically favorable for the atoms to cooperate. An iron atom will tell its neighbor, hey, I'm pointing my magnetic north this way. You should too. And the neighbor listens. And it tells its neighbor, and so on. This creates a chain reaction. Imagine a huge room full of people. In a paramagnetic material, everyone is standing around, facing in random directions. If you play some music at the front of the room, the external magnet, a few people might turn to look, but most will ignore it. In a ferromagnetic material, the people are different. They are all friends. If one person turns to look at the front, their friend next to them will turn too, and the friend next to them. Soon you have whole groups of friends, all facing the same direction. This is exactly what happens in a piece of iron. The exchange interaction is so strong that it causes large clusters of atoms, millions or billions of them, to all align their spins in the same direction. These self-aligned clusters are called magnetic domains. Now, a regular unmagnetized nail you pick up off the ground is made of iron and it's ferromagnetic. But it won't stick to your fridge. Why not? Because while it's made up of these magnetic domains, the domains themselves are pointing in random directions. One domain, a huge cluster of aligned atoms, might be pointing up. The domain next to it might be pointing left. Another one might be pointing down. On the whole, the magnetic fields of all these different domains cancel each other out. The nail has no overall or net magnetism. This is where making a magnet comes in. To turn that iron nail into a permanent magnet, you need to get its domains to line up. One way to do this is to take a strong permanent magnet and stroke the nail with it, always in the same direction. The strong magnetic field of the permanent magnet will pull on the domains inside the nail. The domains that are already mostly aligned with the field will grow larger, taking over neighboring domains that are pointed in other directions. The walls between the domains will physically move. Domains that are pointing the wrong way will shrink and might even flip their orientation entirely to align with the field. After you've done this enough, a majority of the magnetic domains inside the nail will be pointing in the same direction. Now, all those tiny atomic magnets are no longer fighting each other, they are cooperating. Their individual magnetic fields add up, creating one large, strong magnetic field that extends out from the nail. You have made a permanent magnet. It will now stick to your fridge all by itself. The permanence depends on the material. In a soft iron nail, the domains are easy to move. You can magnetize it easily, but it will also lose its magnetism easily. If you drop it or hit it with a hammer, the shock can jolt the domains back into a random arrangement. In hard, magnetic materials, like the alloys used in good quality permanent magnets like neodymium magnets, the crystal structure of the material makes it very difficult for the domain walls to move. Once you force them to align, they get stuck in that position. It takes a lot of energy to mess them up again, which is why they are strong and permanent. You can also destroy ferromagnetism with heat. If you heat a magnet, you are giving its atoms more and more thermal energy. They start to vibrate and jiggle more and more violently. At a certain point, this jiggling becomes so energetic that it overcomes the exchange interaction that holds the domains together. The atoms break free from their neighbor's influence and start pointing in random directions again. The domains fall apart, and the material loses its magnetism. The temperature at which this happens is called the Curie temperature. For iron, it's about 770 degrees Celsius. Above that temperature, iron stops being ferromagnetic and becomes merely paramagnetic. If you let it cool down, the domains can form again, but they'll be in a random arrangement, so it won't be a magnet anymore unless you remagnetize it. So, ferromagnetism is about two things: unpaired electrons and a powerful cooperative effect, the exchange interaction, that makes them all want to line up together in domains. Just to make things more complete, there are a couple of other more obscure types of magnetism that are related to ferromagnetism. One is called antiferromagnetism. In these materials, like chromium and manganese oxide, the exchange interaction is still there. Neighboring atoms still talk to each other, but instead of telling their neighbors to point in the same direction, they tell them to point in the opposite direction. So you get a perfectly ordered pattern of alternating spins: up, down, up, down, up, down. Because for every up spin, there is a down spin, their magnetic fields cancel out perfectly. So, even though there is a huge amount of magnetic order on the atomic level, the material as a whole has no net magnetism. It's a hidden kind of magnetism. Then there's ferromagnetism. This is a bit of a hybrid. It's like antiferromagnetism, where neighboring atoms want to point in opposite directions. But in these materials, the atoms creating the up spins are not the same as the atoms creating the atom spins. One set of atoms has a stronger magnetic moment than the other. So you have a pattern of alternating spins, but the up spins are stronger than the down spins. They don't cancel out completely. Like, there's a net magnetic moment left over. This is what makes the material magnetic. Many of the magnets we use in everyday life, especially the dark, brittle, ceramic ones called ferrets, found in fridge magnets and cheap speakers, are actually ferromagnetic, not ferromagnetic. They are good, strong, and cheap to make, but they are generally not as powerful as the best ferromagnetic metal alloys. So let's step back and see the whole picture. Magnetism isn't one thing. It's a spectrum of behaviors that all start with the electron. Every material responds to a magnetic field in some way. Every material is at least diamagnetic, weakly repelled by a magnetic field because the field alters the electron orbits. If a material has atoms with unpaired electrons, it's also paramagnetic, meaning its random atomic magnets can be temporarily and weakly aligned by an external field, causing a slight attraction. But for the strong magnetism we see and use every day, you need something more. You need ferromagnetism or ferrimagnetism. This requires not just unpaired electrons, but also a special quantum mechanical interaction that makes neighboring atoms cooperate on a massive scale, forcing their magnetic fields to align into large domains. An unmagnetized piece of iron is a collection of random domains. A permanent magnet is a piece of iron where the majority of those domains have been forced to point in the same direction, combining their strength to create a powerful, lasting magnetic field. This entire phenomenon, from the invisible push you feel between two magnets to the data stored on a computer's hard drive, is a macroscopic, large-scale consequence of a tiny, fundamental property of a single subatomic particle, the spin of the electron. The way those spins are arranged, like randomly, weakly aligned, or locked together in massive cooperative domains, determines whether a material is a piece of wood, a bit of aluminum, or a powerful magnet. It's an amazing link between the quantum world, which we can never see, and the everyday world we touch and feel. It's not magic, it's the deep, strange, and beautiful physics of how our universe is put together. The silent force holding a note to your fridge is the echo of countless electrons, all spinning in unison.